Hello, it's Ryan. Today we're going to talk or finish discussing electric force, and we're going to introduce electric fields for you. And the way I often like to do that is to recall or at least remind you of the force due to gravity, which is really the first action at a distance force that we had to deal with. Remember, action at a distance forces are spooky forces because they reach through space and time, and bodies get affected by them, accelerated by them, without any actual physical contact between the bodies. And so that baffled physicists for a very long time. The way we kind of ended up coming up with a solution to that is an idea called fields. So there are gravitational fields and electric fields, and eventually magnetic fields that will allow us a mechanism to explain where those action at a distance forces are coming from, or better yet, where the energy comes from when something has work done on it by those forces. So that's kind of a lot to take in, but throughout the rest of this discussion, it'll make more sense, I think. So what we're first going to do is recall, and maybe for some of you, this might be the first time you've seen it, and that's okay, gravitational force. Now, what we would do in Physics 1, instead of talking about gravitational force like that, we would just call it a weight force, because everything that we were going to work on in Physics 1 all kind of took place in general at the surface of the Earth. And so the acceleration due to gravity was a constant value for anything at that position. So maybe we could say weight from Physics 1, weight was equal to mg, and that's how we would discuss the gravitational force. But actually, if we wanted to use the Newtonian representation of the force due to gravity, it would actually look like this, where we have m1, m2 over r squared, and the direction would be radial, so we put an r hat vector there. We could note that g is a fundamental constant of the universe. It's called the gravitational constant. And g is equal to 6.675 times 10 to the negative 11 Newton meter squared per kilogram squared. And so something to note for gravitational force is that it's always attractive. It must happen between two bodies with mass, like the equation implies here. Mass 1, mass 2. You have to have two bodies with mass in order to have a gravitational interaction between them. The gravitational interaction between them will always be attractive, and so it will always point toward the bodies. So diagrammatically, you could show that we might have M1 and M2, and each of those would experience a gravitational force, Fg1 and Fg2. And as you can see, these are attractive forces, and they're equal and opposite in direction, as Newton's third law always promises. So I always like to note, in order to have this in order to have this gravitational force, there must exist a gravitational field. And we say that the field stores gravitational potential energy. And then we could note that the G field, the gravitational field, is a mathematical entity, and it allows us to predict the behavior of massive bodies near other massive bodies. That allow us to predict the, we'll say the effects a massive body has on other masses. And so in general, like for our Earth, Mother Earth, there it is, very blue. Not as blue as Uranus, believe it or not, but still very blue. There's Earth. Earth will have a gravitational field, a G field for short, that is radial and always pointed toward the center of the Earth. And so as you see, we could show many, many lines, but they should all be pointed toward the center, and they should all be just lines that represent the gravitation. And so the idea is, if you have a massive body like Earth, and then another massive body like the Moon, then they affect each other with a gravitational force. The Earth will be pulling on the Moon, Fg on the Moon, and the Moon will be pulling on the Earth with an equal and opposite force, Fg on the Earth. And I think I screwed up my picture above. I'll fix that. And this is really the phenomenon that allows the Moon to orbit the Earth. Actually, the Moon and the Sun are both just orbiting, the Moon and the Earth are both just orbiting the Sun. But we, from our perspective, feel like the Moon is orbiting us as well. And that's due to this gravitational force. As you can see, I accounted for Newton's third law. If the Moon has a gravitational force pulling on it, keeping it bound to the Earth, then the Earth has a gravitational force on the Earth based or because of the Moon, and they're equal and opposite. Do we feel this gravitational force due to the Moon? Maybe you don't feel it, but we do experience it. This is the reason that we have high tides. When the Moon is above the surface of the Earth, the gravitational force from the Moon pulls on the surface of the Earth, and what it does is it pulls the water from the oceans toward it. That will in fact lower the tide on the sides. This would be low tide, this would be high tide. And if you think about gravitational force being dependent on distance, then you know that way over here, the gravitational force will be less than on the other side of the Earth, and so the tides will rise there too. And as the Moon orbits the Earth, our tides change. Well, is it because of the orbital motion of the Moon, or is it because of the revolution, the rotational motion of our Earth? I bet it's that one. Anyway, something to think about. And gravitational fields are always attractive, and they're the explanation as to why we stick to the Earth. So these were wrong, and I apologize. Really, these should have been attractive, like I said. And so M1 would be attracted to M2, and M2 would be attracted to M1. So please fix your notes. I'm used to making little mistakes like that and having people correct me in class, but no one is there to correct me right now. So that's a little input into gravitational force, the way that we would actually want to calculate it if we weren't in Physics 1, and the explanation as to why that action at a distance force exists. It's a gravitational field. We're not really going to work with these in Physics 2 very much. I just like to introduce fields with one that you're very used to being in. You're not as familiar with electric or magnetic fields yet. Okay, so that was gravitational force. So we're going to get back into electric force, which we use Coulomb's law to describe. And I'll just remind us that the electric force was Q1, Q2 instead of M's. But as you can see graphically, that's why our fundamental force diagram had the shape of electric force and gravitational force exactly identical to each other. We did note, though, that this is very large, 10 to the 9, 9 times 10 to the 9, whereas this is very small, and so we can see that the gravitational force is going to be weaker in general than the electric force. The electric force is also radial, but we can't say that it's always attractive, right? Electric force can be attractive or repulsive. And so I'm just going to close this discussion out on forces with our final notes that I want to give you on electric force. So just a couple little brief notes. The first one I like to give you is to remind you to see your fundamental force diagram. Next, we want to note that usually we just ignore signs on the charges when calculating the magnitude. And then I'm going to note, allow diagram to show which vectors are negative and label accordingly. So just a reminder, that's something that students forget. Finally, the last interesting point I like to make is that the electric force depends on a fundamental constant of the universe, and it's epsilon naught, which was the permeativity of free space. I may have misspelled permeativity. I'm sorry, I'm kind of rushing. Permeativity of free space. And what that tells us, what that explains to us, or what that's supposed to describe is how electric fields propagate through a vacuum. This is how electric fields propagate through a vacuum. And epsilon naught is equal to 8.854 times 10 to the negative 12 Coulomb squared per Newton meters squared. So that's just a fundamental constant of the universe. And if that was different, then we think everything else would be different as well. Gravitational force is also dictated by a fundamental constant. We gave it the letter G, and it's always this value. So these action at a distance forces, we use fields to say why they work, and we use fundamental constants of the universe to help us describe how powerful or what the magnitude of them would be. So that's all my preface and intro into why we want to look at these things called fields. They help give us a reason for action at a distance forces. And we're not going to talk much more about gravitational fields. We may reference that it's always attractive and radial, but we're not really going to use them. What we're interested in our class are electric fields. Electric fields. So in general, electric fields, and we write electric fields, I'll often abbreviate it like this. Electric fields are vector quantities, like electric force. So electric fields need both magnitude and direction, and they exist in and throughout space-time. But this is actually a big argument in physics. Do they actually exist or not? You can't go to Meyer and buy a jar of field lines. So Arguably, these fields don't exist. They're just mathematical entities that allow us to predict behaviors, like I said before. So electric fields, they exist in and throughout space-time and propagate at the speed of light. So they travel through space-time, or at least through a vacuum at the speed of light, which is dictated partially by or dictated entirely by this constant. At the speed of light in a vacuum. That's speed of light. We're going to say that E fields exist due to anything with charge. E fields exist due to anything with charge. So a body that, anytime we talk about a charged body or a point charge, then we know right away that those charges must be creating an electric field around the body that we're talking about, in and throughout space-time. Okay, so anyway, E fields exist due to anything with charge. They allow us to predict the behaviors of charged particles. And we are talking about them like they're real things, but really they are just mathematical entities in order to make these predictions. So I say they allow us to predict the behaviors of charged particles, but really they are only mathematical entities that we will, of course, represent diagrammatically and with math. That's a little redundant, but it's okay. Okay, so that's generally what an electric field is. I'm going to make another note here before we move on, though, and it'll make more sense as we start to do some diagrams. But like I said, they exist due to anything with charge. And so what we want to talk about is how you will analyze an electric field. So we'll say we analyze an electric field by placing a positive test charge. I'm going to underline that. By placing a positive test charge near or around the charged particle or particles, creating the E field. We're going to say the electric field direction is defined by the potential motion of the test charge. And I'm going to show you this, so this will all make sense. And after I say test charge, I'm going to put comma, because we always call the test charge Q sub O. So just before we go on, we'll say Q sub O is defined as a positive test charge with negligible size and mass. With, we'll say actually just negligible observables. Negligible observables. Size, charge, mass. So the only really point of this test charge is that it's positive. So we will look at what the effects on some positive charge will be around other charged particles. So we're going to say mathematically, we have an electric field equal to the electric force divided by our test charge. So I'm not going to define Q sub O again. It's defined right here. I'm not going to rewrite that. But I'll define that E, so we'll say where E is the electric field. It will have the same direction as the electric force on our positive test charge, and Fe is the electric force. So let's say electric field vector and electric force vector. But on this one, I'm going to say the electric force vector on Q sub O. So if you were to take this equation one step further, we could substitute in Coulomb's law, but I'm not going to do that yet. That's going to be for a specific electric field. So we're just going to keep this as our general definition for any electric field. I'm going to give you a few more notes, and then we'll show you some examples of electric fields produced by different forms of charged bodies. Okay, so one note that I'd like to give you. This is kind of just an interesting point, that the electric force is a result of the two electric fields produced by two charged particles. So the electric force is the result of two electric fields produced by two charges. So that's one little note, and then a few more, so I'll do a few more. Electric fields can be electric fields in any volume of space will superpose or add together. So we'll say electric field, and this is true of any vector really, so it's not actually as new as it may sound. Electric fields superpose, oops, I'm sorry, not superpose, that's silly, someone must be hungry. Superpose, which is a fancy word for add, together to create a total or net electric field. And so mathematically speaking, we could say that E net, the total electric field in some volume of space, is the sum from I equals 1 to n of EI. And so that would be E1 plus E2 plus E3, and so on, until you get to En, the last electric field in that volume. Notice that we're adding vectors, and so what you might note is that x direction and y direction will be added independently. So we'll say are analyzed independently. And you're used to that because we were doing it through all of Physics 1. Two more notes for the electric field, and this will all come together, I promise. The electric field is always in the direction of the electric force on Q sub O. So we'll say E is always in the direction, and I did say this before, I just really want to drive it home, in the direction of Fe on the test charge Q sub O. And then finally, which this is another one that might sound elusive right now, but it'll come together, the electric field strength can be represented by field line density. And I'll come back and show you exactly what that means after our first diagram of an electric field, which is what we're going to do now. So we're going to look at electric fields diagrammatically. And so another way to think of this is that this will be the electric field produced by specific geometries of charges. So this will be the electric, so we're going to start with the electric field produced by a positive point charge. Not test charge, by a positive point charge. And so this is a little different. A positive point charge can have a mass that we would have to account for if we were asked about it. This is a real thing that could exist, like a proton or an electron, only it wouldn't be an electron, it'd be a positron if it was positive. So the electric field produced by a positive point charge is the first thing we're going to do. I'll make our positive point charge right here. There it is. I'll give it a plus sign to indicate its positivity. And I'm going to go ahead and use this dark blue for my field color this time. Actually, I'll use it for my Q sub O. So this is, you don't have to go into this memorizing how an electric field looks, though you do know it's radial. So for this positive point charge, what we're going to do is we're going to place our Q sub O, a positive test charge, there, anywhere really, but we're going to place it first right there. Now knowing that this Q sub O is a positive charge and that this is a positive charge, what would the electric force have to be? Would it be attractive or repulsive? They would be repelling each other because they're like charges. And so I'm just going to show that this positive test charge will experience an electric force, Fe, due to that positive charge that's repelling it away from the positive charge because they're the same positive sign, so they repel. Now I could put the positive test charge somewhere else, maybe right here. If I move the positive test charge closer to that positive point charge, would the electric force get bigger or smaller? Well, remember the electric force, Fe, it goes like 1 over r squared. So if we make the denominator smaller, then the electric force would get larger. And so we could show that with a longer arrow, Fe. If we wanted to, we could continue along this line. But I think what we would show is that anywhere on this line, the electric field should be pointed away from the positive point charge. And so this would be an electric field line. And I could continue to do this. I could put a positive point charge right here if I wanted. We know that that would cause a repulsive force, and it's going to be a little smaller than this one. So we know it'll be repulsive and away like that. And so that gives us the direction of the electric field produced by that positive point charge. And so if I just continued to do this, I could show that this electric field, due to a positive point charge, will look very much like our gravitational field, except for one attribute. Our gravitational field was attractive, pulling everything toward it. It looks like this. Oops, I got a little bit carried away with my arrows. It looks like this is repulsive for positive charges, and so these arrows point away from the positive charge. So I really didn't have to draw any Q sub O's if I didn't want to. These really don't stay in the picture, but they indicated for us the direction of an electric force that would be there, which in turn tells us the direction of the electric field line that is produced by our positive point charge. So it's radial, it points away, and it always looks like this for any positive point charge. Now what we're going to do is show you the electric field, the E field, due to a negative point charge. The E field due to a negative point charge. Negative's usually represented with black, so I'm gonna, I think that's just because of batteries. Batteries in our next few sections will have red for the positive side of the battery and black for the negative. To analyze the direction of the electric field produced by this negative point charge, we're still going to have to go ahead and input a positive test charge, Q sub O. And then we'll have to decide what type of force will that positive test charge experience due to our negative point charge. Well, if this is positive and this is negative, then this should be attracted to this. And that means it will have a force toward, and maybe a little longer, I don't know, it doesn't have to be perfect, toward that point charge. That would be the Fe. We could do another one if we wanted. We could show one maybe here. That might be a little smaller force, but it still will be attractive. And we could continue on doing this really indefinitely, but what we would end up showing are field lines that are radial again. Radial toward the center field lines. And those field lines will all have that attractive direction for a positive point charge. So all these field lines will be pointed toward the negative, so as you can see, it's radial. It all looks, now this one looks just like a gravitational field, doesn't it? Whereas this looks like a reverse gravitational field. And it's these electric fields that we say store the energy that allow these electric forces to do work on any particle that is put near the positive charge or the negative charge. So that's a diagrammatic representation of the electric field due to a positive or a negative point charge. Something I wanted to bring us back to briefly was the idea of field line density. I made this quick note right at the end that electric field strength can be represented by field line density. Field line density, the way I think of that is the number of field lines in some unit area. So what I can do is I can create like a box of some kind. Oh, I don't know what I'm doing here. I'll just draw it. So if I draw a box like that, that's not a good spot. Okay, bear with me. Here, I'm going to draw the box here and here. And what would help if I just show one more field line? So something that I didn't say is that we've just shown some field lines. Really, this thing will have, infinitely many field lines in a sense. They're all going to be radial, so we could have drawn way more. This field could have been drawn with more field lines, and it would have been just fine. I was just showing some to give the shape. Okay, so looking at these two areas, ideally they'd be identical. They're close enough for us. This area, this orange box, has 2 field lines passing through it. This orange box has 4. So we would say that this orange box has a high, we'll say 4 field lines per area. That's confusing. I don't want to be confusing. This has a higher line density than this one. This one only has 2 field lines. This one has 4. And so what we could argue then is that the electric field anywhere in here will have a greater magnitude or be stronger than the electric field anywhere in here. Now you already knew that because the electric field is inverse square. So you know the closer you get, the stronger it is. But sometimes you'll have to analyze a field with respect to the density of field lines because you might not know enough information otherwise. So that's just what this bullet is talking about. The electric field strength can be represented by field line density. I think it makes more sense now if you think of it like this. If there are more field lines in some area, then you can say that the electric field is stronger there. The last diagram I'm going to draw for us today for electric fields is the electric field due to a dipole. A dipole is kind of just a fancy word for something with two poles. Di is two. Pole represents a charge in this case. So a dipole will have a positive charged side and a negatively charged side. So this is going to be the electric dipole. And we actually talked about electric dipoles in one of our previous lectures when we talked about charge by induction and charge by conduction, and specifically it was charge by induction. When we talked about charge by induction, that's a plus 2q. We talked about when a charged body goes near a conductor or even sometimes an insulator, it can induce a charge without actually allowing charges to change position from one body to the other. I believe I called it jumping ship. But the point is, we talked about an induced dipole in that section. So now we're just going to talk about an electric dipole in general. And I'm drawing it for you. It's got one side with a negative Q charge and one side with a positive 2Q charge. So in other words, this one has twice as much positive charge as this has in negative charge. I'm going to go ahead and use this blue for my electric field lines. And I'm going to show you how these electric field lines, how we would use the point charge system still to get them. And then I'm going to magically have the field appear. So if we wanted to figure out what an electric field line looked like, we could place a positive point charge inside of this electric field somewhere. There it is, Q sub O. And what I'm going to do is I'm going to show the electric force due to Q, the positive charge on this positive test charge. And then I'm going to show the electric force on this positive test charge due to the negative charge. And then we'll add those together because vectors add together. So for the positive charge, I've chosen red because I wrote it in red. And it will be radial, and it will look something like this, right? We don't know exactly what it will be, but the electric force on that positive test charge will be repelled by that positive charge, because like charges repel. So Fe is like so. Now the electric force due to our negative charge on our positive test charge would be attractive, because if this is a positive test charge, then it will be attracted to the negative charge. And it will be smaller, won't it? It will have less charge to be attracted to, and it's much farther away. When we add these forces together, we can show that our resultant will look like that. That would be Fe on our positive point charge. And if we continued this analysis, we could do a lot of different positive point charges and show that in general, the shape of this electric field line will look something like this. And you always give the direction of the field with those arrowheads. And voila, there are the electric field lines that we could have slowly but surely figured out using positive test charges. So as you can see, all the electric field lines leave our positive point charge pointed away, and all of the lines coming to our negative point charge are going toward the negative. Something else that I tried to really do was I tried to show that because this is a positive 2q and this is a negative q, this should have twice the field line density when you're near it than this one. And so I was careful to try to have twice the number of field lines here than I did here. Something weird to think about is the idea that there may be infinitely many field lines leaving in all directions from each of these point charges, but there still are twice as many, infinitely many, coming from this one as there are from this one. The idea of infinity has baffled mathematicians and scientists since we discovered the idea itself, and so don't feel bad if that don't make no sense. Anyway, there's a couple little other points to make. This isn't a bad picture. I'm not the best artist, but this really does show the general shape of a dipole. You also can always look these things up because you have the internet. Something I wanted to show was if you were to take a look at this from really far away, so if your distance r is very large, then you wouldn't see this two-charge dipole system anymore. So when we say very large, there might be a distance d between these, and what we mean by that is that r is much greater than the distance between them. If you were to look at this from far away, in other words, you shouldn't really see a system with two charges. If you look at a forest from far away, you really just see one big green blur. And as you get closer, your eyes are able to resolve the individual trees. And that's kind of the same here. If we get far enough away, our eyes or our sensing mechanism won't be able to resolve that this is two point charges anymore. All it will see will be the net charge of the system. Well, if we add +2 to -1, we get +1. So when we get far enough away, then we know that this should look like just a positive Q charge electric field. A positive charged electric field should be all radial lines pointing away. So when we get far enough away, that's what this little double tick on the right side of the screen is representing. If we're close, we know that the field will look as it's shown, but if we get far enough away, the field should just look like this. So that's just something to keep in mind, and that's what I tried to represent with the double dash breaking up that field line going into our negative charge particle. So that's probably long enough for this video. That's a lot of concepts for electric fields. I'll release one more video that kind of analyzes the mathematics you'll need and then goes through an example for you.